This conference will now be recorded.
Yeah, dear students, so in the last session, we have discussed about joint distribution and joint density functions, and also marginal distribution and marginal density function, how to represent them, and what are the properties of joint distribution and joint density function, and how to derive the distribution and density functions, that is marginal distribution and marginal density functions, and how to plot them we have seen in the last session, and by using a problem, right? And also by using the density function, how to find different probabilities is also discussed in the last session with the help of problems, right? So now let us move on to conditional distribution and conditional density function, right? So in the first chapter, we have discussed about conditional distribution and conditional density function, and but there we have mentioned that there are two methods to define conditional distribution and conditional density functions, right? So here basically the conditional distribution and conditional density functions will come into the picture if at all if there are conditional probabilities are available in any experiment, in the sense if any one event is depending on the other event, right? When in such a scenario you are going to define the joint probabilities. If at all if you have the joint probabilities, you can define the conditional distribution and conditional density function. That is, you are going to apply conditioning on the random variable x or any random variable, right? So in the first chapter, as we were discussing about single random variable, we have taken the conditioning on the random variable by the event taken from the same random variable. That is, if at all if the random variable x is conditioned by an event b, that b will be the event selected by using the same random variable x. That is the case we have taken in the first chapter, and there we have taken again two cases. One is point conditioning, other one is interval conditioning. In the similar way, we are going to discuss the conditional distribution and density function with the two cases, point conditioning and interval conditioning, in this case also. But the only difference is, in the first chapter we apply the conditioning by using the event which is taken by or defined by using the same random variable, but here that event is defined by using a different random variable, right? So let us see how to define, right? So here the conditional distribution function of a random variable x given some event b is defined as, so it is the conditional distribution function for the single random variable case. That is, fx of x given b is equal to probability of x less than or equal to x given b is equal to the joint probability of x less than or x and b, that is p of x less than or equal to x intersection b by p of b. So this is the formula derived in the case of single random variable in the very first chapter of your subject PTSP. Right? Now, for any event b with non-zero probability, this relation is valid. So now the corresponding conditional density function also derived. So in there, how do you write? The conditional density function is small fx of x given b is the differentiation of the above function, that is conditional distribution function of the random variable x. This formula is also derived in the first chapter. So now let us move on to here. If the event b is, so as I said, you can define the event b in two ways. One is point conditioning, other one is interval conditioning. And remember here, the b is an event selected by the same random variable x in the case of single random variable scenario. Here the b is an event defined by using different random variable in this scenario, right? So first, point conditioning. Point conditioning in the sense that event is defined by using just a point from the random variable y. Point from the random variable y in the sense that event is selected as the b, let the event b is defined in terms of y such that it has some specific value, only specific value y, such that b equal to y minus delta y less than or equal to y less than or equal to y plus delta y. Only just a particular point, that is particular point with the length, differential length delta y minus delta y to y plus delta y, where delta y is infinitesimally small value. Delta y is infinitesimally small value, or I can say where delta y is a small quantity that eventually approaches zero. That is called infinitesimally small value, right? Therefore here, since the y is continuous random variable, I am taking like this, right? But therefore for this event, conditional distribution can be written. Why? Because for the continuous random variable, you cannot select only one particular point. An interval you can select, and I am making that interval as a point here by letting the delta y as almost zero, right? So therefore, the conditional density distribution function can be written like this: fx of x given b. What is b now? Y minus delta y to y plus delta y. Y minus delta y less than or equal to y less than or equal to y plus delta y. So which is nothing but fx of x by fx of y. Capital Fx of x by capital Fx of y, or simply you can write like this: integral y minus delta y to y plus delta y, integral minus infinity to x, fx comma y of fx comma y of temporary variables eta, that is e1 e2 de1 de2, by integral y minus delta y to y plus delta y fy of eta eta. In fact, we have seen the relation or the representation of distribution function, conditional distribution function, in the very first chapter. I'm just modifying a little bit here by taking the event b as y minus delta y less than or equal to y less than or equal to y plus delta y. So that is, actually it is the joint, that is the conditional distribution function is taken by applying the conditioning with the event from the other random variable. So therefore here the joint density function is coming into the picture, the joint density function, right? So that is, the joint density function is small fxy of, that is eta1 eta2 d eta1 d eta2 or de1 de2, right? And what are the limits here for x? That is, these are the limits for x and these are the limits for y, right? And here these are the limits for y, as we are supposed to find. Take fy of y here, and in fact this is derived, this formula is already derived. I'm taking just the same formula as it is from the first chapter, right? Now if at all, if the random variables are discrete, for the discrete random variable, ultimately here x and y values will be in the form of small xi and small yj, where I is 1 2 3 up to n. Similarly j is maybe 1 2 3, maybe let us take up to m, right? If at all, if x and y both are discrete random variable and their probabilities are denoted by p of xi and p of yj usually, right? And the probability of the joint occurrence of xi and yj, that is the joint probability, is p of xi comma yj. That is the joint probability, right? So then how can I write the conditional function? Generally the density function I know how to write for the discrete random variable. Small fi of y equal to summation j equal to 1 to m p of yj del of y minus yj. And I know how to write density function, joint density function. As I know density function fy of y and joint density function fxy of x comma y, again I am taking the same formula from the first chapter for representation of distribution function, conditional distribution function of discrete random variable. And here, now suppose that the specific value of y of interest is yk. As I said, conditioning is applied on x by using the event taken from the random variable y. In the continuous case, the event is y minus delta y less than or equal to y less than or equal to y plus delta y. Why? Because directly I cannot define the point in the case of continuous random variable. But in the case of discrete random variable, I can take the point, a particular point. Let the point be y equal to yk, right? On substitution into the conditional distribution function, that is, we can write like this: fx of y equal to yk. In the same formula, I am just replacing the conditioning term as from y minus delta y less than or equal to y less than or equal to y plus delta y to y equal to yk. So ultimately here it becomes fx of x by the denominator will be not fy of y, it is fy of yk. Only at that particular point that distribution value is taken. In the previous case, the distribution value is taken in the interval. Therefore, the integration of y minus delta y to y plus delta y was coming to the picture. But now here it was there in the expression, right? So now here we have a particular value. Therefore, the particular value of the distribution function is nothing but p of yk into del of y minus yk, right? Since it is discrete random variable, and the numerator will be integral minus infinity to x summation I equal to 1 to n the probability p of x. That is, what is this actually? Nothing but the joint density function summation I equal to 1 n p of xi yk del of x minus xi del of y minus yk dx, right? Or I can write simply like this. One is why? Because the integration of unit impulse becomes unit step, right? Unit impulse becomes unit step. My intention is to get fx of x. Therefore, I'm just eliminating y variable, right? So y variable. Therefore, I'm taking the limits for dy as from minus infinity to x. Am I clear? Therefore, finally, I can rewrite like this. By here, del of y minus yk is independent of I here. It is coming out of the summation. These two gets cancelled. As a result, I can write the general expression for conditional distribution function. You need to remember this formula. That's it. You need to remember conditional distribution function for discrete random variable case is fx of x given y equal to yk equal to summation I equal to 1 to n joint probability p of xi comma yk by p of yk into u of x minus xi. Similarly, I can also write a density function, right? How do you write the density function? The density function is by applying the differentiation to the distribution function, I can get the density function. Is it right or not? By applying the differentiation to the distribution function, I can derive the density function. So this is distribution function, conditional distribution function. After deriving, the final expression is summation I equal to 1 to n p of xi comma yk by p of yk into u of x minus xi. And after differentiation, if I apply the differentiation on both the sides, it becomes small fx of x. With respect to x, if I take the differentiation, it becomes small fx of x. With respect to x, if I apply the differentiation, the whole term. Why? Because the numerator value is probability, denominator value is also probability. Both are constants, and the only function term is with respect to the function which can vary with respect to x is this particular unit step function. The unit step function differentiation will be unit impulse function. Therefore, here the conditional density function is equal to summation I equal to 1 to n p of xi yk by p of yk into del of x minus xi. Understood how to write the conditional distribution and conditional density. The only thing is you need to remember the conditional distribution and density function, which is discussed in the very first chapter. Then you can easily derive here, right? You have to remember the two formulae. Next, coming to the continuous random variables, here if x and y both are continuous random variables and delta y is very small quantity, then conditional distribution, we have taken this already, right? So what is this actually here? What is the actual formula here? So this is the formula here. This is the actual formula. Even you can simplify this. How do you simplify this? And just remember the denominator term. And the denominator term is what? If let both x and y are continuous random variables and delta y is very small quantity, then the conditional distribution function can be written like this. That is, the denominator is, earlier we have integral y minus delta y to y plus delta y, fy of y dy. So now after the integration, we have got like this, fy of y into 2 delta y, not dy dx, right? So here also we got the same substitution here. And finally, you can write the expression like this also. Generalized expression, integral minus infinity to x, small fx comma y of eta 1 y d eta 1 by fy of y. I repeat, the distribution function of x by conditioning it with y equal to y is equal to integral minus infinity to x fx y of eta 1 comma y d eta 1, where eta 1 is temporary variable by fy of y, right? Similarly, the density function also can be taken. So here we have integration. If I apply the differentiation, integration and differentiation gets cancelled. Directly you can write small fx of x given y equal to y. The only change here is if I assume that delta y is 0, almost 0. If delta y is not 0, you cannot write like this. If delta y is 0, conditional function can be like this. Conditional density function will be equal to small fx of x given y equal to y. Here it is not the interval, that is y minus delta y to y plus delta y. It is direct point by letting delta y to 0, right? It becomes fx of x given by, which is equal to fx comma y x comma y by fy of y. So finally, what are the expressions for conditional distribution and density functions for the discrete random variable? I repeat, for the discrete random variable, the distribution function is summation I equal to 1 to n probability joint probability p of xi comma yk by p of yk into unit step function u of x minus xi, as I am deriving for x. Similarly, the density function equal to conditional density function equal to summation probability joint probability p of xi yk by p of yk into unit impulse del of x minus xi. And coming to the continuous random variable case, directly you can write that the conditional distribution function equal to integral minus infinity to x fx comma y of eta 1 comma y d eta 1 by fy of y. Density function is small fx of x given y equal to fx of x given y, shortcut, is equal to fx comma y of x comma y by fy of y. Four relations must be remembered. Conditional distribution and density functions of discrete random variable case and continuous random variable case. Am I clear? And it can also be shown like this. Fx of x given y. If I apply conditioning to random variable by y by using the event taken by using x, here applying the conditioning on x by y. If it is reversed, that is applying the conditioning on y by using x, ultimately the density function will be fx comma y of x comma y is fx of x. It is very important relation. The density function, conditional density function, is very important relation. Please remember this, right? Next, that is about point conditioning. Coming to the interval conditioning in the sense, we have taken the conditioning with either in the discrete random variable with yk, in the continuous random variable in between delta y, that is y minus delta y to y plus delta y. If delta y is 0, finally it is assumed as y only. But here the scenario is different. We consider the event as ya less than y less than or equal to yb. That is, an interval is taken for applying the conditioning. If event b is defined for a specific interval of random variable y as follows, it is known as interval conditioning. That is, b equal to ya less than y less than or equal to yb, right? So in such a scenario here, and always the probability of that particular event must be non-zero value, then only I can apply the condition, right? Now the conditional distribution function can be written like this. The only change you can observe here is, earlier we used to have y minus delta y to y plus delta y. Now we have got ya to yb is equal to, how do you write here? Directly we have taken fx of x by fy of y. If you remember, fx of x by fy of y. Why? Because it's a short duration term, whereas in this case it is an interval. Therefore this relation can be taken like this. And remember, this is the relation taken from the first chapter, and just take a reference from the first chapter so that you can easily understand the relation. Fx comma y of x given b, fx of x given ya to yb is fx comma y of x comma yb minus fx comma y of x comma ya, right? So that is by fi of yb minus fi of ya. Or I can also write this particular relation as, this can be taken as, from the property integral ya to yb integral minus infinity to x fx comma y of temporary variable eta comma y d eta dy, right? In the denominator, similarly here, since I am taking the joint density function, but here the term is marginal functions, I am making one variable as infinity. Which variable must be taken as infinity? X variable must be taken as infinity. Therefore I am letting the x limits minus infinity to plus infinity, and y limits are from ya to yb, as I need to get the values of marginal distribution function. Am I clear? Right? Density function also differentiation of the previous one. That is, small fx of x given ya less than y less than or equal to yb is. So if I apply the differentiation to this, differentiation with respect to x, ultimately here the integration in the numerator will be vanished. So here I am going to get integral ya to yb fx comma y of x comma y dy by integral ya to yb integral minus infinity to plus infinity fx comma y of x comma y dx dy. Right? Don't be confused. These expressions hold for x and y either continuous or discrete. Why? Because we are just taking an interval. And even if it is discrete also, I'm going to take a particular interval, maybe from 2 to 3 or 3 to 5 or 6 to 7. Like that, I'm going to take a particular interval, not a point. And these conditions are valid for both continuous and discrete random variables. Am I clear? Let me repeat here. So here the conditional distribution function in the case of interval conditioning is fx of x given ya less than y less than or equal to yb. So actually general formula is what here I need to take by using the help of p of a given b equal to p of a intersection b by p of b, right? So here the only thing is a is the event x less than or equal to x, b is the event ya less than y less than or equal to yb, right? The only difference is this one. It is derived from the first chapter only, right? Similarly, density function is also like this. Fx small fx of x given ya less than y less than or equal to yb is integral ya to yb fx comma y of x comma y dy by integral ya to yb integral minus infinity to plus infinity joint density function fx comma y of x comma y dx dy. Please remember the two formulae, right? And let us see example, same example, Game of Thrones, Westworld and other subscriptions from the male and by male and female. And here if you observe, these values are nothing but marginal distribution values, and these are also marginal distribution values or probability values. So usually we define the conditional probability like this: P of A given B equal to P of A intersection B by P of B. For example, a female candidate Noni just got an HBO subscription. What is the chance that her favorite show will be Game of Thrones? Right? Female. So total female subscriptions is 0.54. 0.54. The probability of subscription is 0.54. But out of that, what is the condition here? After female, the subscription is of Game of Thrones show or movie. So that is probability of Game of Thrones when female is subscribing. It becomes 0.24 by 0.54. That is called conditional probability. Why? Because it is P of A intersection B, Game of Thrones intersection female. Right? Similarly here, these are the conditional probability values. Conditional probability values, female candidates and Westworld, and female candidates and other subscription, P of A given B. So by combining all these conditional probabilities, I can write the conditional distribution or conditional probability distribution, and this particular probability values represents the distribution of conditional probabilities. Understood about conditional probability distribution, right? And now we are moving on to a new topic called statistical independence. And in fact, we know the independent event, when the two events are said to be independent, is already a known fact. That is, if I take event as A and event as B, when the two events are said to be independent, it will be recalled that two events A and B are statistically independent if and only if probability of joint probability, that is joint event probability, that is P of A intersection B equal to P of A into P of B. If this condition is satisfied, you can say the two events as independent events, right? Or if I take the example, same example, what is that example? Male subscriptions of Game of Thrones, Westworld and others. These are the subscriptions, and total subscription probability by the male candidates is 0.46. Similarly, by the female candidates is 0.54. And these are all marginal probabilities. Marginal probability of Game of Thrones, marginal probability of Westworld, marginal probability of others, right? The total probability is absolutely equal to 1. So when you can say the two events are said to be independent, for example here, if I take P of A given B, A is what? Let us take Westworld movie subscription, right? And second one is subscription by the female candidates. One event is subscription by female candidate and the other event is Westworld movie subscription, right? P of A given B equal to the conditional probability, that is subscription of Westworld when the female is subscribing. When the female is subscribing, what is the probability of subscribing Westworld? I repeat, what is the action here? A female candidate is subscribing, and when she is subscribing, what is the probability that that subscription is for Westworld? That can be known by taking the probabilities. That is, the probability of Westworld subscription by the female is 0.05 by 0 total female subscription is 0.54. So that conditional probability is 0.093. If at all if P of A given B equal to P of A, then also you can say independent. What is P of A? Actually, A is nothing but Westworld subscription. Westworld subscription is from the marginal probability. The total Westworld subscription maybe by male and female candidates is 0.25. So are they equal? No. Therefore, they are not independent. Or if this is the reality, P of A intersection B equal to P of A into P of B, then also you can say the two events as independent, right? So that is P of westward intersection female. We all know that westward and female 0.05. P of westward is what? Probability of westward is 0. Sorry, probability of westward is 0.25. Probability of female is 0.54. Am I right? 0.54 is the total probability of subscription by the female. P of 0.25 is the probability of subscription for westward. So therefore, if I take the product, it is becoming 0.14. And is it equal to P of A intersection B? No. There also you can say the two events as independent. In that way, you can decide whether the events are independent or not. Am I clear? So now, if at all, if the independent events are existing, you can find out the joint probability. And ultimately, if you know the joint probabilities, you can decide whether the random variables are independent or not, right? See here how this condition can be used to apply to two random variables x and y by defining the events a as x less than or equal to x and b as y less than or equal to y for two real numbers x and y. Thus, x and y are said to be statistically independent random variables. If I take two events, one is A, other one is B, but A is taken as x less than or equal to x, B is taken as y less than or equal to y, then from the same statement taken in the previous slide, that is P of A intersection B equal to P of A into P of B. Similarly here, if that condition is satisfied, you can say them as statistically independent. That is P of x less than or equal to x into P of y less than or equal to y, right? Or you can also write in terms of distribution functions. If at all, if the joint distribution function fx comma y of x comma y is equal to fx of x into fx of fy of y, that is, if at all, if the joint distribution function is equal to the product of marginal distribution functions, then you can say the two random variables are said to be statistically independent. Am I clear? Or you can apply even for density functions. That is, if at all, if the joint density function equal to the product of density functions of individual random variables or marginal density functions, then also you can say statistically independent random variables. Understood? The condition for statistical independence is joint density equal to product of marginal densities or joint distribution equal to product of marginal distributions. Am I clear? And these two are above two expressions serve as sufficient conditions to test for the independence of two random variables. By using the above conditions, even you can take the conditional distributions takes the form as follows. If at all, if they are statistically independent, ultimately what happens, we know that distribution function, conditional distribution function fx of x given y is fx comma y of x comma y by fy of y. If it is satisfied, that is the two random variables are statistically independent, ultimately the conditional distribution becomes the distribution of the random variable x itself. Similarly, the conditional distribution of y becomes the distribution of function of y itself, right? Substituting the condition here. Similarly, density also. Conditional density becomes density itself. That is, the conditional density of x becomes density of x itself, right? And let us take a simple problem here. Consider two continuous random variables x and y with a joint probability density function. Small f of x comma y equal to 2 by 81 x square y. In fact, the same problem is taken even in the previous problem also. Same function is taken in the same previous problem also. But there we have drawn joint probability density function and joint probability distribution function, and also marginal distribution function, right? And probabilities are calculated. But here you are supposed to check whether x and y are independent or not, right? So here, pause the video and try to solve. And there we have calculated k value. In fact, we got 3, k equal to 3. And just go back to previous problem and see the k value. Pause the video and try to solve. And just see the solution now. Small fx of x equal to integral 0 to 3 2 by 81 x square y dy. Why? Because it is what it is. What is fx of x? Marginal density function equal to integral 0 to 3. We are just making, that is vanishing y here. That is, these are the limits for y. It is joint density function. It is in terms of x, 1 by 9 x square. And since k equal to 3, the limits will be from 0 to 3. Similarly, marginal density function equal to 2 by 9 y, right? And as per the condition for the statistical independence, the joint density function must be equal to product of marginal density functions. Let us check here. Absolutely. 2 by 81 into x square y equal to 1 by 9 x square into 2 by 9 y. Right? Absolutely same. Therefore, x and y are independent. Right? And now let us take one more problem. Here, let the joint probability density function for x comma y be f of x comma y equal to 1 by 2 into e power minus y. In the interval, very carefully observe very carefully here. In the interval 0 less than y less than infinity, and limits for y are minus y less than x less than y, right? And equal to 0 otherwise. Find the marginal probability density function of x, that is small fx of x, and find the marginal probability density function of y, that is small fy of y, and check whether they are independent or not, or x and y are independent. Try to solve. Pause the video and try. Yeah. Let us take the solution now. Right, so that is the first question. So we know that marginal density function equal to, when x equal to 0, that is for negative values of x. See here, limits for x are minus y2 plus y, right? If y are taking 0 to infinity, and ultimately here these values will be from minus infinity to plus infinity. Now I am taking for negative values of x condition. If at all negative values of x condition is taken, the limits will be from minus x to plus infinity. Since it is taking from minus infinity to plus infinity, the limits will be from, for y are from minus x to infinity, right? I'm just finding the density function, marginal density function equal to, I am just vanishing the variable y here. And for the y, the limits are, what are the limits for y? Minus x to infinity. Minus x to infinity. If x is less than 0. X is less than 0. Understood? If x is less than 0, minus x to infinity. Why? Because y limits are always positive limits. Why? Because what are the limits for y? Always y are having positive limits, 0 to infinity, right? So therefore the limits for x, the limits for y will be, if at all if x is negative, minus x to infinity. If I integrate, and the resultant will be 1 by 2 into e power x. Similarly, for positive x, no need to worry, y limits are always positive values, therefore from x to infinity, it will be 1 by 2 e power minus x. If I combine the both x less than 0 and x greater than 0, if at all if x is varying from minus infinity to plus infinity, the density function, marginal density function will be 1 by 2 into e power minus mod x. Am I clear? Just try to observe here. Don't be confused. Next, how do you find marginal density function for y? Similar way, fy of y equal to we need to vanish x. What are the limits for x actually from the given data? From the given data, the limits for x are from minus y to y. Directly you can take, right? Y limits are, sorry, x limits are from minus y to y, and resultant is y into e power minus y, where y is varying from 0 to infinity. Am I clear? That's it. What is the condition for statistical independence? Always. What is the condition for the statistical independence? Always the joint density function is equal to the product of individual density functions or marginal density functions. Am I clear? So that is fx comma y of x comma y must be equal to fx of x into fy of y. What is fx of x actually? We have derived the fx of x, that is equal to 1 by 2 into e power minus mod x, whereas fy of y is what? Yes, y into e power minus y. It is not equal. Therefore, x and y are not independent. Finally, right? So now, in this session, we have discussed about conditional distribution and conditional density functions, right? And the conditioning is done by point conditioning and interval conditioning. If the point conditioning is applied for the continuous variables, it will be different, and discrete random variables, it will be different. For both the cases, we have derived the distribution function of the random variable x and the conditional distribution function of the random variable x and the conditional density function of the random variable x by applying the condition by using the event selected by taking the random variable y, right? In both the cases for continuous and discrete random variable. In the interval conditioning also we have selected the event b, but the event b is selected as an interval. But here in this case, for continuous and discrete, both the cases, the conditional distribution and conditional density functions will be same, right? And after that, we have taken the conditions for the statistical independence of random variables, right? For the statistical independence, the joint distribution must be equal to the product of marginal distributions. The joint density must be equal to product of marginal density functions. And we have checked the conditions with the help of problems, right? So here with this we can conclude the session. So in the next session we are going to start sum of two random variables. If at all, if I take sum of two random variables, how do you define the distribution function and density function, right? So in the multiple random variable case, we have taken various cases, but now we are going to take, if at all, if the two random variables are taken, I mean the sum of two random variables is taken and is defined as a new random variable, how to take or how to derive the distribution and density function of the new random variable. All right. So here with this, I'm just concluding the session. We'll continue in the next session. Thank you.